So I want to thank the organizers, of course. I don't think, is Shubro here? Okay. So maybe Shubro is getting a well-deserved rest. So I actually met Shubro for the first time in Japan earlier last year. So maybe, he heard the first version of this talk already. So so I'm a dynamicist by training. I work mainly in mathematical physics. And so what I'm going to talk to you about is deep learning. I've never programmed anything involving deep learning. So what I'm really going to tell you is about what I know, which is a dynamical system. And so it's called the deep linear network, and it was introduced to me by Nadav Cohen, who is currently at the computer science department in Tel Aviv. And there's a bunch of results, and these results are basically with my students at Brown. There's one preprint, or there's one paper out there on the archive. It was published last year, and I'm going to kind of give you a feeling for certain other mysteries. Okay, so it's called the deep linear network. And so what I really want to do is to just do a careful analysis of a gradient flow in the way that somebody in dynamical systems would do. So the deep linear network is a phenomenological model of deep learning. It was introduced by Sanjeev Arora, Nadav Cohen, and Elad Hazan. Just to kind of, so it's a Mickey Mouse model. It's not really a neural network. It's just what you're really doing is studying a linear function. And so it's a gradient flow. And so as in one of the talks yesterday, somebody said a gradient flow involves a state space, a metric, and an energy function. So let me introduce you to my state space, my energy function, and my metric. So our state space is going to be, so D is going to be the dimension of the matrices, dimension of matrix. And N is going to be the number of matrices. By the way, is the sound bothering? Okay, good. Yeah. And so our state space is going to be an n-fold product of matrices. And this n-fold product is introduced to kind of phenomenologically model overparameterization. And so an element in my state space I'm going to represent by a W with an underscore. And this element is a collection of matrices. And so very, very annoyingly for mathematicians, as you will notice, the indices go the wrong way for us, but it's the right way for computer scientists, because what you're trying to model is overparameterization. And so this is going to be our parameter space. This is the space in which the training dynamics will take place. But what we're going to observe is the product of these matrices. Okay, so this is the parameter space. And since I work in mathematical physics, I'll call this the observable. Okay, so let's just do a quick dimension count. So we've got n of these matrices. Each of them is d by d. So a parameter space has dimension n times d squared. And our observable over here involves d squared. Okay, so you're asking yourself, how can you represent a matrix as a product of a bunch of matrices? So our training dynamics are going to live upstairs, but the loss function is going to depend only upon this W. So E of W is going to be our loss function. And we're going to pick a very, very simple problem to think about for the loss function. So just to be concrete, I'm going to think about matrix completion. So let's say simplest case is matrix completion. And let me even make it diagonal matrix completion. Okay, so let me assume that I'm given parameters A1 through AD. And let me set E of W to be equal to 1/2 sum I is equal to 1 to D, WII minus AI squared. So what I'm doing is I'm fixing a bunch of entries D, and my energy function is 0 when the diagonal entries of W are equal to that. So if you take anything like this this would imply, so if W is equal to this tells you that E of W is equal to 0. Okay? So the problem is pretty straightforward. This is our state space. This is our energy function. Our state space is basically like Rn with a very, very big N. So we are sitting in a high dimensional space. We just do a gradient flow of this damn thing. Okay, so the gradient flow is so let me write it out first in the fancy cryptic way. Okay, so where this, W without the underscore is the product of all of those guys. And so this is really living in, so it's n squared equations. So that's our ODE that we're studying. But in fact, that ODE, let me rewrite it as the following. So this is just a computation. You have to do a computation. So the computation really involves just the degeneracy. So I've got an energy function, which is some quadratic function of this sort, could be a more general energy function. The point is that the energy function depends on the training parameters only through the product. And so you have to do like 3-4 lines of algebra. And when you do these 3-4 lines of algebra, what you find out is that for each of these guys, the associated equation you get is, so this is just a computation. Where this guy is a matrix. It's exactly what you think it is equal to, and over here 1. So I love this problem because it's super, super concrete. So the story is basically the following. So in 2018, I was a member of IAS, and I was visiting my host, Dilelis, and Sanjeev was also there that year. And so one day, like Sanjeev was like, you guys know something about differential equations. Let's talk to you. Or he asked Camilo that, and Camilo was like, you know something about applied math. You also show up in my office and we'll have a conversation. And so they showed us these equations. I was like, it's a gradient flow, man. Come on, how hard can this be? Gradient flows have been around in mathematics since 1930 when Marston Morse was studying gradient flows. A pretty major theorem in dynamical systems, or kind of pretty foundational, and it's not that hard to prove. You can find it in my lecture notes on my website. Is a theorem called the LaSalle invariance principle. And the LaSalle invariance principle basically says something like if you've got an energy function which is kind of going up as you go out to infinity, so if you've got an energy function with compact sub-level sets, then as t goes to infinity, your gradient flow is going to converge to something. So I looked at this problem, I was like, come on, this is like LaSalle. This has been known since the 1960s. How hard could this actually be? So of course the problem over here is the following. So standard, by which I mean 1960s, theory of gradient flow. Sorry, I prefer the blackboard to the whiteboard, so I'm kind of screwing up my writing a bit. So standard 1960s theory of gradient flows gives convergence as t goes to infinity, provided E has compact sublevel sets, which really means something like you look at the set, let's say W such that E of W is less than or equal to A, must be compact. Okay, so if you had an energy of this sort, then you would be fine, but this is not true. Okay, so let's get a very, very simple sense of kind of how non-degenerate the energy function is. Sorry? Oh, it's just a standard Euclidean matrix. I'm looking at the, so Frobenius norm on each of these spaces. So, so the metric of, so the norm over here would be, let me write it out this way. Sigma, so sum over all of these guys. So let's say P is indexing. So sorry, I should be careful about my index. So P over here, so this is for 1 less than or equal to P less than or equal to N. So this index, the index P is the depth along the chain. The chain rule, just the chain rule, just the chain rule, nothing more. So you do the chain rule, it's a cute calculation. It's a cute calculation. These are actually Jacobian factors coming in. Let me make a comment on that in just a second. Let me just finish up the thought over here. Trace WP transpose WP. So, simplest possible norm that you can take. So this is literally 3 lines of calculation, but you have to get your indices right just to come up with these factors. And actually, let me, the point I forgot to state. So one of the things to note over here is that this is just the calculus of the overparameterization tells you that the gradients of energies of this form are always of this sort. So the space of gradients is at most of dimension d squared. So we're living in this high dimensional space, n times d squared. But if I look at the vector fields generated by gradients, the vector fields are a very, very thin set. They have only d squared dimensions. That's kind of the point. So this talk is really about just this fact that you've got gradients which are thin within a high dimensional space, and that you've built up an energy function which has a lot of invariances. So if I have a fixed W over here, I can find many, many different ways of writing it out as a product. So there's an overparameterization structure, and so all of this talk is about the interplay between the overparameterization structure, there's a kind of group theory that underlies this, and just more and more detailed analysis of this thing. Absolutely. Absolutely. Yeah, I know. So yeah, that's the training. So exactly this. So I'll do more of these dimension counts. It becomes kind of simpler. Okay. And let me also just kind of give you a sense of it's not just a loss function, but matrices have interesting properties. So you try to understand stuff like the rank. So let me give you an example of the simplest case. So I'll actually say something about this simple energy function. So here's a typical example. So consider 2 by 2. So d is equal to 2. And let's say, let's just choose this energy. So let's say A1 is equal to A2 is equal to 1. So we are looking at this energy function. 1/2. You can write it out completely explicitly. Okay, so I've got this like super simple energy function. And so let me kind of try to write out, so let me make a picture of the 4-dimensional space. So, W is now W11, W12. Okay, so I've got this quadratic function on a state space which is R4, and I want to know where this quadratic function is equal to 0. Well, it's going to be 0 if this guy is that. So let's just look at our zero energy surface is just this plane. But even within this plane, there's a little curve over here where let me think about that as, think about this. Let's call that x and 1 over x. So it's equal to 0, of course, on what I wrote out earlier, but there's within the kind of space where the energy is 0, there are little manifolds, so this would be rank 1 matrices. So, I'm becoming more and more specific. So I'm saying that I've got this energy is super degenerate. Now I'm looking at the set where the energy is 0, and I'm foliating my set where the energy is 0 by rank. Okay. So now you say, it's the basic question over here is you've got a gradient flow, pick some initial condition, let it go. You want to know where it goes. So typical observation, as t goes to infinity, so you've got some point, it's kind of like the other, like the W, so like this is the W1, W21, W12 space. There's also the W11, W22 space. So let's assume that that's in this direction, kind of becomes 0, 0, 0. And as t goes to infinity, you kind of end up on the rank 1 matrices. Numerical observation, no proof. Okay? So super simple dynamical system. This is what we observe. We can't prove it. Yeah. Pick a typical initial condition, it ends up on low rank matrices. So Nadav showed me this phenomenon, and I was hooked. But I was like, okay, I'm not that hooked. I gave it to a grad student. The grad student played around with it for 2 years, and then he came back to me with interesting formulas, and then I was hooked. So I'm going to show you these formulas. Yeah?
N is large in this example?
No, this is n is equal to, I could do this with n is equal to 2. I could even just do this with n is equal to 1, and you observe this phenomenon. Okay, so let me begin to state some theorems. The first one, going back to Aurora, Cohen, and Hazan. And then, since I'm a dynamicist, I'll draw pictures, and then it'll get more and more interesting, I hope. So let me rephrase what I was saying. So first I was saying general theory does not tell you without a proof that you've got convergence. Okay, so you need to do a little bit of work with that. And given that you've got convergence, you actually want to know where you converge to on the zero energy surface. And the empirical observation is that you're converging to low rank matrices. That's what you really want to explain. Okay. So one of the first things you do when you study dynamical systems is that you want to understand how your phase space looks. How is it foliated in some way? And Sanjeev, Nadav, and Elad made a kind of interesting observation. So I just need to state a definition, and then I'll state the theorem. And then I'll do a dimension count so that we can begin to understand this better and better. So consider n minus 1 symmetric matrices. Okay, and let me denote them. Let's say G n minus 1, G n minus 2 through G1. And define the variety. Okay, so variety is kind of fancy word. Just define the solution set to a bunch of equations. And let me call it M script G. So let's call that. Okay, so what's this variety going to be? It's going to be the set of matrices W that solve star, where star is a collection of equations of the form WP plus 1 transposed WP plus 1 minus WP transposed. So these are D by D matrices, and with D by D matrices you have left and right symmetric, left and right polar decompositions. So it kind of comes in different orders. Okay, so I've got a collection of equations. Somehow you just find this collection of equations. So this collection of equations, I've got n minus 1 times d plus 1 over 2 equations. Okay, this is a symmetric matrix. That's the dimension of symmetric matrices. And I've got n minus 1 of these equations. Okay. So that's just a definition. Let me make a picture to help you think about this. So what you're really solving is quadratic equations, and what you're really obtaining is conic sections, but it's a conic section within a space of matrices, but it's a conic section, so you can kind of try to make a schematic picture of it. A kind of picture that, let's say, here's our big space. And within our space, if I fix all of these G's, I've kind of got, let me draw things like, kind of like hyperbolas, so cones, conic sections, really. Okay, so each of these is an mg. And there's one special guy over here, which I'm going to just call m0. Okay, so here's the theorem. This is due to Aurora, Govind, and Hazan. Okay, it's not stated in this language in their work. I'm going to state it in the dynamicist language. The theorem is that mg, so each mg is invariant under gradient. I'm going to need notation for my gradient flow equation, so let me call that sharp W dot. Okay, so this is the kind of thing that gets a dynamicist hooked. So you're trying to understand a dynamical system, you're trying to foliate your phase space and understand what's going on. So we've got the space of matrices, they're kind of evolving under the dynamics. And what the theorem says is that, okay, start out on this guy. And if you start out on this guy, you're always going to stay on this guy. I'm foliating the space of parameters. That is my phase space. Oh, no, you're thinking Hamiltonian system. So let's just say phase space just big, okay? I think there's a Hamiltonian structure underneath it. There are clearly group invariances. I don't, there's structure. It'll become clear. There's more and more structure, okay? So it's this theorem is literally 2 lines to prove. And it goes back again to the same basic equation that, like, there's the overparameterization. You do the change of variables. It's a 2-line calculation. You do this calculation, and the theorem pops out. Typically in dynamical systems, it's really like an invariant manifold theorem is typically a tough theorem. In this case, it's not. So there's a space, and so clearly, amongst all of these, you'd think that this, there are all these cones out there, and there's one which is very, very special. And so they gave it a name. And so we're going to focus on that guy. And I'm going to tell you a couple of properties about that guy. So they called it the balanced manifold. It's not really a manifold because it's got this singularity. But I'm going to kind of abuse notation, or let me call it maybe the balanced conic. So I'm being recorded, right? Yeah, okay, so let me make a controversial statement. So the paper is lovely, okay? So paper has, so this is a kind of CS paper, and there are 2 statements. Okay, so one statement is a theorem. The theorem is that this manifold is invariant. And the second statement is any initial condition converges to the balanced manifold. So there's a theorem that says that, okay, or an observation. So observations. You don't actually solve the differential equations when you're doing numerical simulations. You're doing numerics. So what actually happens is that when you do the numerics, somehow you're ending up on that guy. Okay, I mean, this is a bad picture. What you're really doing is choosing your initializations carefully, a small Gaussian matrix or something like that, and you let it go. But if you pick a random initial condition, it's going to be somewhere on this phase space. It's not going to be sitting on this with probability 1. But when you run the numerics, as t goes to infinity, what you typically find is that you end up on this balanced manifold. So we have a kind of interesting contrast. So there's a theorem that says that the dynamics, if you're doing it kind of exactly, is kind of preserving each of these is preserving this foliation structure. But then when you actually do the numerics, somehow this guy is stable. So this, I'm going to focus on properties of the balanced cone or the balanced conic. I'm going to show you some kind of beautiful mathematical structure that this balanced conic has. And in some sense, the mystery I'm really trying to understand, and I think this mystery is actually the core of how to take the DLN and take it to true training dynamics in deep neural networks, is really related to kind of understanding what the hell is so special about this M0. Okay, so let me just pause for a second to check that you guys are with me. If anybody's got a question. Yeah, Philippe. Exactly. Exactly. And it's not really a manifold just because of the singularity of the origin. Okay? So the empirical observation, yeah. So actually there's a part of, what you gain from it is really it's not just variety, it's just defined by quadratic equations. So you can just do calculations. So one of the amazing, so this is a fantastic model. It really is. I don't think I spilled any coffee this time, thankfully. So it's a fantastic model. It really is, because you can kind of keep hitting it by different methods. And it's always forgiving in the sense that you get some, like we've computed the tangent space of this thing like 5 different ways. So there's definitely a part where the algebraic stuff helps you. You use singular value decomposition, you think about it different ways and you get kind of different insights each time. But there's also a sense in which it should not matter and your intuition is completely correct. And I keep thinking that there's a kind of equilibrium picture. So tomorrow I actually want to do stochastic dynamics and give you a feeling for why this is important. But today I just kind of want to show you properties, like just kind of mathematical miracles that seem to be coming out of this. Some proved by us, some proved by other people, just to give you a feeling that clearly this is very, very special, and we just want to understand it for that reason, because yes, some of it being special is that we can analyze it because it's given by quadratic equations, but we believe that there's kind of deeper phenomena behind it that we'd like to understand. So what it really gives you is it's a model that allows you to penetrate more and more of the geometry, and kind of the piece of the geometry you're really trying to understand is that you're moving in very thin directions, but you've got a bunch of symmetries because of over-parameterizations, and kind of the intuitions like, what if your noise is all in the kind of tangent directions, what you get out? Yeah, so Praneeth, yeah. Yeah, yeah, pretty much. Yeah, that's it. So in some sense, so one of the ways I'd like to think about it is that the discrete steps are kind of giving you small noise at each step, and somehow that's the way I'm actually going to model it, and in that context, I can prove different theorems. So I won't prove theorems, but I want to think about it as there's noise. What's the effect of noise within the system? So there's noise coming from the initial conditions, but actually I also believe that there's kind of noise coming from the rounding errors or something like that, and that there's structure that's coming out. So we really want to understand why this is special, and we really want to understand how to generalize this to DLN, to deep neural networks. The stuff that I showed you about the thin directions, the formulas, those are Jacobian formulas, and that works totally fine for an arbitrary deep neural network. Yeah. So yeah, we will do, it won't be independent of the dynamics. There'll be a coupling between kind of, what I'll show you is that the variety has nice mathematical structure, and this nice mathematical structure is very, very closely tied to the dynamic structure. So let me get to the next theorem then. Yeah.
Actually close the loop, right? So here you go from 1 to n minus 1, but if I actually call wn plus 1 w1.
I'm not sure, right? I'm thinking about, so the reason for not closing the loop is you're really thinking about function compositions. And of course, what you're really saying is I've got a linear function, that's why it's the linear net. So I've got a linear function and I'm making my linear function through composition. So that's why you really want the product structure Wn through W1. I don't quite see what the meaning would be.
It's relevant. I'm just asking it
This one's hard enough. Or at least this one's interesting enough. It's rich enough to just keep you tantalized and kind of still give you enough space to breathe each day. Yeah, was there any, yeah, sure. Excellent. So, okay. So that's exactly true. So there are what you're picking up is actually one of the special properties of the balanced conic, which is not true. So on the balanced conic, it's certainly true that what happens is that all of these guys are 0. And so, of course, what you find is that the singular value of every single matrix along the chain is identical, but that's not sufficient. So it's certainly true that if you're balanced, all the singular values are the same, but that you can use that observation to get one parametrization, which is. So that's exactly right. So we'll begin to play with rotations, but not just this moment. So I still have stuff to say. Yeah. Okay, so it's not necessarily the case. So that's a great question. Actually, the DLN works in general. So in fact, in Nadav's, the first paper, like what you really need is just that you can define the matrix product, right? So you can do that in generality. Further, for some of the theorems that I'm going to be stating over here, I'm actually going to be assuming that all of the W's are invertible. In fact, you actually have a much richer structure related to kind of foliation by rank. Okay, but let me actually do a little bit more and state like the second theorem. I want to state at least 4 theorems today. So, and we're halfway in. So, let me kind of state the second theorem. Okay, so the empirical observation is that t goes to infinity. So let's call this gradient descent. Tends to M0. Okay. So now let me give you a second theorem. And now I'm going to kind of improve that picture or change that picture to a second picture. And I'm going to draw 2 pictures, an upstairs and a downstairs. And then I'll give you a definition and then I'll state the theorem. So now our picture is going to be like this. So I've got M0, there's one of the other manifolds. So this space is MdN, so that's n times d squared in terms of dimension. And then downstairs over here, so let me make it this way, is, okay. So associated, so the point over here is called W underscore, and downstairs is the W. And I've got a mapping, a projection mapping that's over here. And so pi is by definition just this guy. Okay, so what I'm really just doing is saying that pi of W is equal to this W. I've got a mapping from, so this is where the dynamics is taking place. That's the observable. And so what our theorem is telling us is that if we start out over here, theorem 1 is telling us, this is kind of theorem 1. That's the dynamics is over there. And so if I'm following, so if I've got this W of t, then of course down here, I've got an associated W of t. Doesn't seem that special. But here's a lovely theorem. Proven by okay, all of these are very, very recent papers. So that one is 2017. This one is maybe, I think in print, it's like 2022 or 2021. So this is by Ba, Rahout, Justiger, and Westickenberg. So their theorem says, it kind of gives you a kind of dynamic reason why the balanced manifold or the balanced conic is special. They say, W0 belongs to, so that's the initial condition. Then the solution so what I'm doing is I pick an initial condition upstairs, I solve my differential equation upstairs, and then I look at the observable along that trajectory. So pick an initial point over here, look at the trajectory associated to it, and let's look at the associated WT down here. Then the theorem is that the Riemannian gradient flow W dot is equal to minus grad Gn E of W, where, so let me write it out first in the fancy way, and then I'll give you is the metric on MD given by submersion. So in general, there's no reason to even have a closed equation downstairs. But in fact, not just you get a closed equation downstairs, but your closed equation downstairs is a gradient flow, and the associated metric for the gradient flow is exactly the natural metric that you would get downstairs by basically a machine called Riemannian submersion. So what that really means is that you compute the null space associated with this mapping, and you squash the directions in that null space. Okay. So I'm going to give you formulas for this metric. So it's kind of like now you begin to see that there's interesting stuff going on. And I think one of the trends I was pointing out is a bunch of us who are trained in dynamics and analysis are clearly moving towards data science problems. So Michael Westigenberg and I were both postdocs with Felix Otto a long, long time ago. And so when we look at gradient flow dynamics, we're just trained to look for the metric. And so Michael, I guess, was working with Holger Rauhut, and he just kind of said, like, okay, you've got a gradient flow. You need to think carefully about the metric. And here's what the metric is. Okay, so the idea of Riemannian submersion, for example, is there in kind of Otto's famous paper on the geometry of the distributive evolution equations. And so I find it really lovely that in this kind of simple model of deep learning, you see exactly the kind of canonical structure that you should be looking for. So the metric is down here. So what's happened is there's a space. So actually, let me make that picture a little bit better, right? So that's a great question. So over here, what I've got is upstairs, I've got, let me write it this way as, let me write it this way. So this was kind of like Euclidean space over here, and now what's happened over here is that I've got MDGN. So this space down here, the space of matrices, has been enriched with a metric. And in fact, actually, this is, there's a kind of finer version of this theorem, which is actually a foliation by rank. So in fact, you can foliate the space over here by matrices of kind of various ranks. And in fact, you'll get a kind of stratification of this space down here by metrics, which are kind of stratified by rank. Okay? And this theorem holds in exactly that generality. So these theorems, one of the interesting things about these theorems is that once you kind of get the right idea, it's not hard to prove. In some sense, the issue is kind of seeing the structure and then kind of just putting the pieces together and cranking it out. Yeah?
Which one of the MGs are local minimum?
Mg is just a variety. It's got nothing to do with the energy function.
Right, I guess they're very big, the gradient is zero. Because I'm asking which ones are actually local.
No, again, so the energy is defined on this guy down here. So the energy is changing as I'm moving over here. You're completely correct that there are the tangent directions are obtained from the quadratic equation, but the varieties over here have nothing to do with the energy.
The original properties.
So I'm saying exactly the same thing again. So this is the geometry. The energy function is not playing any role in these theorems. So any energy function you choose, as long as the energy function depends on this W, only through the product, you will have the structure. So the manifolds themselves have nothing to do with the energy. The manifolds are just defined through these quadratic equations. So it's not meaningful to say manifold is, saddle point or anything. It's a manifold. The energy varies along that manifold. It's invariant under the dynamics, but the energy is not constant on the manifold. Sorry?
The gradient is.
The gradient is not zero. The gradient is that
You're just doing the same,
you're just staying on the same manifold.
Oh, okay, sorry.
Yeah, yeah. Yeah, Philip.
What do we know about this metric? Like, do you know the equations? Like, what do we know about it?
Let me give you a theorem. I was like, nobody is going to, oh yeah, so let me show you formulas for the metric and then let me give you a theorem. Yeah. I would suggest you turn around and ask Robert. Robert's like the world's expert on Riemannian submersion. Yeah, the question is like, what is Riemannian submersion? Okay, let me put it this way. So, okay, here's one way to think about it. So there are two canonical ways of getting a new metric from Euclidean metrics. So one way would be what's called immersion. So if I'm sitting on this manifold over here, then it's got a metric because it's sitting on that space. It's sitting within a larger space. Okay. So the other way, so with Riemannian submersion, what's going? Okay, let me make a. Okay, so what you want to do is, okay, so okay, this is a clean way of thinking about it. So associated to each point over here, there is, let me kind of make a slightly arbitrary picture. So associated to this point over here, there's an entire orbit or an entire set that projects down to this point. Okay, so if you're looking at distances on this space, you've got distances in these tangent directions, and you've got distances in those perpendicular directions. So you want to take that perpendicular length and move it down here, and the tangential piece you want to squash out. Okay? So that's basically what Riemann is. So you have to write out the formulas for it, but that's basically what it boils down to. Okay, so you take the null space and the perpendicular space of this. You take the null space and the null space, and you take the perpendicular to it, and the metric is just the perpendicular piece pushed down. It's one of the canonical ways of getting a new metric from an old metric. Philip, did you have a question? Sorry? Okay. Is there any other question? Okay. So it turns out that this metric has all sorts of special properties. So let me kind of give you a feeling for it. So the way these guys actually got it, so here's a formula for the metric. So let me try to make that explicit. So there are several different formulas. Let me give it to you in one of the ways that they first wrote it out. So let me perhaps just try to understand that. So now I'm sitting in my space with this metric. And so what that means is that I'm sitting at some point over here. I want to look at a tangent vector, so let me call it Z. And I want to associate a length to this vector Z sitting over here. So over here, Z belongs to the tangent space at W, that guy. So the formula is a little bit of a mouthful. But what we do is define the map Z to A and Z. So it's a linear transformation. And this linear transformation is defined in the following way. So AN acting on Z is 1 over capital N, sigma B is equal to 1 to N. W transposed to the, I may screw this up, 1 minus B. And yeah, I do feel like I'm making this up at this point. It's something of this nature. There's a clean formula. And so the length, G and ZZ, so this is the squared length in the new metric of this guy, is the trace of Z transposed ANZ. Okay, so it's a kind of slightly complicated looking formula, but you can actually massage it, rewrite it using the polar factor, using the polar factor or singular value decomposition of this matrix. The point is that there's a relatively clean formula. So there's a kind of geometric way of thinking about it using Riemannian submersion. But what that actually boils down to is that you actually have to compute what the Riemannian submersion is. So you have to compute this null space, et cetera, and at the end of it, you get a formula over here that pops out. Okay, so the formula is like, I want to find the length of a vector in the tangent space sitting at this matrix. So I compute this linear map, and then I compute that guy, and I'm done. And it's enough to get the length of any vector, because by polarization, you can pick up the inner product between anything else. 4 minutes left? Okay. Okay, I didn't really get very far, but let me just kind of give you a sense of one of the things that you can do. So here's a theorem that we proved, and it's related to the kind of low rank phenomena. So this is a theorem by Govind, me, and Rasto. And this is from, I guess, last year. Volume form of the metric Gn, or actually, let me start this way. So actually, let me kind of make, rather than write it out Gn, let me kind of just note the following fact. One of the things that you can do with the formula of this sort is like you're trying to understand, so you're trying to do deep linear networks. So one of the things that you can do with this model is that you can kind of make sense of something called infinite depth. The way you make sense of infinite depth is you let n go to infinity in this formula. You've got a sum. The sum becomes an integral. So the infinite depth limit. Okay, I actually want to state two things. Okay, maybe I won't state the metric first. So there's a very nice formula for the volume form, which is something coming out of random, like it's very similar to formulas coming out of random matrix theory. You get a formula for the volume form in terms of random on determinants. Let me tell you actually something much more interesting, because that'll give me a kind of lead in to the next lecture. So punchline of this talk is that there's this invariant manifold structure, there's this balanced manifold. Let me tell you something very, very special mathematically about the balanced cone, and then we'll stop for today. Let's just do this in the simplest case. N is equal to 2 and D is equal to 2. And let's look at, so now W is simply W2, W1, and let me write out W1 in the following form, right? Let's just try to get a handle on what this manifold or this cone actually is. Okay, so we've got this cone, or this conic section, that's now sitting in R8, and so W0 is contained within R8. And so it's going to be given by 3 equations. So let me write out those equations, and then I'll tell you something fascinating about these equations. X1 squared plus X2 squared. Sorry, this seems a little tedious, but there's a moral at the end of it. X1, X3 plus X2, X4. Sorry, is this unreadable? So this is X8. Okay. X6 squared, X7 squared. Okay, so the equation WW transpose is equal to, or W2 transpose W, there was a matrix equation I've just written out in coordinates. And so what we've got is a solution set for something sitting in R8. And let me now add equation 1 plus equation 3. What you get is the collection of equations x1 squared, x2 squared, squared. Okay, so it turns out that this collection of equations is super famous in the calculus of variations. This is something called the Simons cone, introduced by Jim Simons in the late 1960s. And this cone is super important in the theory of the calculus of variations. Because in the theory of calculus of variations, what you're trying to do is do the minimizer of the areal function. So think about soap bubbles. You want to say that the minimum shape of a soap bubble is like going to be a sphere. So you want to say that if you're minimizing an area functional, you've got a smooth surface. It turns out that this theorem is true up until R7. So up until 7 dimensions, it's true that if you're kind of minimizing the area functional, you will be smooth. It turns out that in 8 dimensions, this is not true. And this is the counterexample. So this is one of the fundamental counterexamples in the calculus of variations. And it blows my mind. So Camilo de Lellis is like the world's expert on this stuff. And Sanjeev came into his office and actually showed him this, and he didn't get it. So it really makes me happy. So it turns out that this balanced cone, it's just really got some crazy mathematical structure that we don't understand. And so I find this fascinating because it's like this problem coming out of deep learning, a model of deep learning, and somehow there's this kind of amazing persistence of absolutely classical and traditional mathematics. So this is the phenomenon. So it's clear on empirical grounds that the balanced cone is interesting. Our balanced cone, in the simplest case, d is equal to n is equal to 2, is a subcone of this famous object. And so we really just want to understand what this balanced cone is and where it's coming from and what on earth it has to do with curvature. So that's what I'd like to give you a feeling for in the next talks. I don't have full theorems, but at this moment, when I saw this equation, I was completely hooked on this problem. So I think it's a gift that deep learning has given, like mathematicians like me. There's this beautiful dynamical system, and this beautiful dynamical system just has a structure. And so we get that this balanced condition, which was found by Sanjeev and co, is very, very important in this model. And what we're really trying to understand is the conceptual importance of this balanced manifold, because that's what we want to translate back to true deep learning. So there is some structure over here, and it's just fascinating. Okay, so it's 2:53. Oh, okay. Was I supposed to? Okay, that sounds fine. So I'll take questions. That's cool. Yeah, Philippe.
So the Westerkamp theorem that says that
Yeah. Absolutely. Yeah. So yeah, that's exactly it. So in some sense, that's where we're going. So we're really looking for foundations of geometric deep learning. So in some sense, that's exactly where we want to go, where we want to say that, okay, if you're doing true deep learning, downstairs you've got a function space. This is your energy. So actually all of the stuff with your matrix completion, etc., all of that is phenomenological, and you can map it back to true function approximation. You've got the Riemannian submergence structure where you pick different parameters and it leads to the same function. What's missing is somehow the understanding. So in this problem, like all of the stuff, there's these symmetries upstairs, and you can really get a handle on the symmetries upstairs using your dimension counting. You begin to see products. So you actually, I'll show you entropy formulas tomorrow, maybe, if I have the time in 1 hour. So, we really see that the Riemannian submergence structure is very, very robust. What we don't have in a robust way is an understanding of the concept of the balancedness. What we really have is a collection of theorems on the balanced manifold, each of which is evidence. So these theorems, it's okay, I'm speaking as a aesthete. So they're bunch of beautiful formulas. Beautiful formula for the balanced manifold, beautiful formula for the volume forms, beautiful formulas for group orbits. So you see the stuff upstairs, but when you try to push it, we don't feel like we have, even at this point. So I'm whatever, I spend 20% or 25% of my time on this. I still don't feel like I can see that balancedness is the right condition, but I don't see how to think about balancedness in the true deep learning setting. I'm thinking about it algebraically, and I don't want to think about it algebraically. I want to think about it somehow structurally, conceptually, and that's still a bit missing. So, yeah. Yeah. Okay, so I'll do stochastic gradient descent tomorrow. Yeah, absolutely. So so what I'll show you tomorrow is actually an insight, kind of where I relate stochastic gradient descent and mean curvature, because over here there's a kind of minimal curvature aspect, and I'll kind of show you how to get mean curvature out of stochastics. It's not kind of finished for this problem, but it's finished for kind of related problems. So the intuition I can try to communicate. Yeah. Yeah.
You alluded to the infinite depth limit.
Yeah.
Is there a natural limiting object?
Oh, so that's a super question. So it turns out, so this is a kind of another lovely fact. So it's one of these models where like you can, so it turns out that all the formulas, so you can compute these volume form formulas, and these formulas all become cleaner as n goes to infinity. So there's some super clean formulas for the infinite depth limit, but of course the upstairs has degenerated completely. It turns out that the infinite depth limit is related to something called the Bogulyubov metric in quantum mech. So somehow there is, again, this kind of lovely formula. With hindsight, it's not that strange, because in some sense we've built in all of these symmetries, because you're taking a matrix and asking how can you write out the matrix as a product of a bunch of matrices. This is a very clean mathematical problem. Like, sure, it came out of deep learning, but it's just a clean mathematical problem, so it's not that surprising that it would have clean structure. But still, the kind of layers of the structure, like the ways in which it fits with Riemannian submersion, fits with volume formulas, fits with the freaking Simon's cone, it's kind of way richer than I expected. So, yeah, Philippe.
How much of the structure is
coming? So it's kind of funny you mentioned that, because actually with d is equal to 1 is the first, so about 3 years ago I was trying to understand like what on earth is this deep learning stuff, and I was talking to Yanis Kavrakidis. He's like, oh, let me explain to you what overparameterization is, and he showed me d is equal to 1. He's like, okay, take this function, write it out as a product. But the non-commutativity really, the matrix nature just makes it infinitely richer. I was at a meeting in CMAT 2 weeks ago where there were kind of a bunch of people from free probability. And, like guys like Boris Hanin have been kind of looking at, so over here, when you have this problem, you want to take an n going to infinity limit, you want to take a d going to infinity limit, you want to see what the formulas are. So, yes, it feels like everything is related to non-commutativity, that without the matrix element, d is equal to 1 would be kind of completely cheap. But actually, even in the d is equal to 1 case, you kind of see the Jacobian formulas. You see pieces which are still meaningful. But the finer Jacobian factors, et cetera, like you really have to do kind of the group invariances in there. It's nothing is fancy in some sense, but it's clearly related to the matrix nature. Like even over here, like you have 3 equations, not 1 equation. So this is really the matrix equations. That's in some sense an R8 equation. So non-commutativity is definitely kind of bedrock in there. I don't know how to relate that to, I don't know how to relate that to anything, like it's a kind of philosophy statement. I don't know if it's really.
Yeah, but I mean.
That's true. That's exactly right. So I really see it as kind of generalized. So I see it really as just much more. So let me put it this way, right? So I see it as just a kind of meeting point of 2 mathematical communities. And the way I would really think about this is like, so actually one of those guys, this guy is like Delalis' student. And the kind of question I asked him is like just look at the balanced cone. Look at the system of equations. Can you prove that this is a minimizer of the energy function? That's the point of the Simon's cone. It's minimal, so minimal really just means zero mean curvature, but it's a minimizer of the energy function. So what's happening over here is that I'm giving you a collection of guesses for minimal cones within spaces of matrices, and a natural conjecture to ask is the balanced cone a minimal cone always? So that's a calculus of variations question, and it's a non-trivial calculus.